Hello, I'm David. I'm one of the lecturers at the Maths Learning Centre, and this is a rough and ready lecture about derivatives and tangents. In the previous lecture, I talked about derivatives, the process of differentiation, and I ran out of time and I didn't get to talk about tangents. And so I'm doing a special one just about tangents, a shorter one. No, sorry. In the previous lecture, I showed this picture where there's a curve created by a function, this function here, and I've got a view window that I can move around on this curve, and the little window here will show me what it looks like when I zoom in. And I can zoom in quite a bit and see what it looks like when I'm close by to the function. And if I zoom in far enough, then it looks like a straight line. This function, when I'm very close to it, is almost straight. There are some places where it's not so straight, and I can zoom in even further, and it is nice and straight when I'm very close to the function. So the idea of the derivative was, if I wanted to have an idea of what the slope of this function was, or the slope of this curve, I can use the idea of what it means for a slope of a line. For the slope of a line, I can do the change in y compared to the change in x. Because for lines, if you change the x the same amount every time, the y changes by the same amount. And as long as I zoom in far enough and use a small enough piece of the curve, it will be almost a straight line. And so that's what a derivative is. A derivative is a formula that tells you for each value of x what the slope of the line is when you're very close to the curve. And so we call that the slope of the curve, the instantaneous rate of change of y with respect to x. And it's basically this idea. But a question we didn't answer in the last video is, what is the equation of this line? If your function really is very close to being this straight line, then nearby to that point, I could just use a straight line to tell me how to figure out what the x and the y's are. And that might be a useful thing to be able to do. And so that's what we'd like to do. At every point, we'd like to create a line which matches the slope of the curve at that point. And that line is called a tangent. Tangent has another meaning, but we'll see that soon. So let me do this just with 1 point on one graph. Here is a graph. It's f of x is equal to x to the power of 4 minus 12x squared plus 19x. And it goes up pretty fast when I'm far away from when I've got big x's. But I'm going to specifically just look at 1 point. This point just here, 2, 6. So let me zoom in. So there's the point 2, 6 on the curve. And I'm interested in what the slope of the line is that matches the slope of the curve here. So if I zoom right in until my line curve looks straight, it's getting there, nearly straight. Okay, so on this scale, it really does look like a straight line. And this line, I can see it passes through the point 2, 6. See the coordinate 2 and the coordinate 6 there. And as I go across 1, it goes up 3. So the slope of this line is 3. So it goes through the point 2, 6, it has slope 3. It should be possible to figure out the equation of that line. It should be, I could either write it as, something x plus something equals something, or I can write it as y equals something x plus something. There's different choices. I should be able to figure that out. And that's a skill we're going to need to be able to use in order to find tangents generally. So I'm going to do an example of that over on the paper. Okay, so this is a skill we're going to need. We're going to be able to have to find equations of lines. And we're going to use the slope and a point it passes through. So just basically I'm going to do an example. So suppose a straight line has slope 3 and passes through the point 26. Find an equation for the line. Okay, so this is the line that I'm looking for in the picture there, but it works as a good example generally. Okay, so the slope and one point it passes through is enough information to find the equation of a line. So there are various versions of the equation of a line, and one of them does actually include the slope, and so it's not the worst one to use as my first version of the equation of a line. So I know that the equation is y equals mx plus c. Most people call it mx plus c. You could do ax plus b. It doesn't really matter what letters you use. And importantly, not everyone uses the same letters for this, so you need to tell the person reading it what these things stand for. So the equation is that for some m and c, and also where m actually turns out to be the slope. And so therefore we can say that the equation is y equals 3x plus c. And the whole point of an equation for an object is that every point on the object satisfies that equation. If I sub the point, any point that's on this line into this equation, it will work. Whatever the y is will be the same answer as whatever 3 times x plus c is. And what that's going to allow us to do is figure out what the c has to be in order to make it work. So we know 2, 6 is on the line. So the 6 must be equal to 3 times 2 plus c. So in this case, we get 6 equals 6 plus c, which means that the c has to be 0. I never managed to fit it all on one page. Therefore 0 equals c if we subtract 6 from both sides, and so the equation is y equals 3x and the c is 0. Now you won't always have the c come out to 0. That's a coincidence. Sometimes it comes out to something else. And I'll do several other examples where it does come out to something else. But this is something that we're going to have to be able to do over and over, so it was a good thing to start. So let's go back to our example. And let me draw the line y equals 2x. Or 3x, sorry. And there it is. It's right on top of my function at this point. And that's the point, right? It was designed to be the correct slope and pass through that point. So what if I zoom out and see what it looks like when I'm not quite so close? I can just start to see at the edge here the curve is not right on top of the straight line anymore. Oh, here it goes. The curve moves away from this straight line at this point. But the nice thing is this line only meets the curve in this region at that point. That's the traditional meaning of tangent. A tangent is a line that just sits on your curve at that exact point. So the idea being that if you were following along the curve here like this, then at this point you could, if you stopped following the curve and just went in whatever direction you were going, you could go out this way. And this line works in both directions. It's very close to the curve here and meets it exactly at that one point only, and then the curve moves away from it. That's what a tangent is. Okay. So what I'm going to do is I'm going to do a little bit of magic, and I'm going to turn these off and use some of the skills I'm about to teach you to create the same line and tangent, and zoom out just a little further and see that we can figure out what that tangent is at every point. Like that. And at every point, no matter where it is, if we zoom in far enough, we can't tell the difference between the line and the curve. That's the idea. Okay, so why don't we do some examples of attempting to calculate the tangent to various curves. Well, to functions anyway. We'll get onto general curves in a minute. So, if you're trying to find tangent to a curve, we've already seen how we did it in the picture. We're going to need to find the correct slope for our line, and it turns out that the correct slope is the derivative. That's what the derivative does. It tells you the slope of the little piece of line which is very close to your curve. So that's sort of the method that is going to be useful, and you don't necessarily need to do it all in this order, but it's what we're going to do. So the slope, so to find a tangent to a function y equals f of x at the point x equals a, first we're going to need a slope and a point that it passes through. So the point that it passes through is the point where the y-coordinate works out to be f of a. So we can say find f of a, then the tangent passes through a f of a. 2, find f dashed a, then the tangent has slope f dashed a, and 3, find the equation of the line. And that'll do it. Okay. So, I mean, you don't have to do it in this order. Obviously, it doesn't matter which order you do these two things in. And there are some times where it's a little easier to see what's going on, and you can just write down the equation of the line. And if you're very experienced in line equation formats, there are some times where you can just write it down from the information you have. And actually, I may or may not even show you that to you. I'll think about it. No, I won't. No, I will. But first I'll do one in the same method of finding a line that I did already. So let me pick a random function and do it. Find the tangent to y equals x cubed minus 2x plus 1. Actually, let me make it a bit more complicated than that, eh? I reckon we can do complicated derivatives. X cubed plus 1 minus x at the point where x is equal to 2. All right. So let's see what happens, eh? We're going to need to find the equation of a line, we're going to need to know its slope, and we're going to need to know a point that it passes through. So far we know the x-coordinate of the point that it passes through, so we can now find the y-coordinate. So when x equals 2, y equals the square root of 2 cubed plus 1 minus 2, which is the square root of 8 plus 1 minus 2. which is square root of 9 minus 2, and 9 is 3, which is 1. Neat. Okay, so the tangent passes through 2, 1. Okay, and we also know that the derivative, now interestingly when I describe this I call it f dashed, but remember that you can do the derivative, write the derivative as dy on dx just as much as you can call it f dashed. And this story didn't mention an f, so I don't want to mention it now because otherwise I'll have to tell the reader what f is. So I'm just going to do it as dy on dx. Okay, so just a second, it's going to be too hard to do dy on dx from that version. I really should rewrite my function like this. Okay, so the derivative of that, if it was just an x, would be a half to the minus a half, because minus half minus 1 is minus a half. The x cubed plus 1 will still be there, and I'll have to multiply by 3x squared, because that's the derivative of what's on the inside. And then the derivative of minus x is minus 1. Okay? Okay? So just might be a little easier to calculate this if I just simplified it a little bit. The 3.5 can be a 3 over 2. The x squared, that minus means it's actually on the bottom, and it'll be square root x cubed plus 1. And when I say on the bottom, I mean really this thing all by itself is 1 over x cubed plus 1 to the half. But when I do 1 over times x squared, well, the x squared will end up on the top. So I've sort of skipped a lot of the working there. Minus 1. Okay, so at this point, at the point where x equals 2, I can figure out what dy on dx is. So when x equals 2, dy on dx is 3 on 2 times 2 squared on 2 cubed plus 1 minus 1. Now actually, we already figured out earlier what the square root of 2 cubed plus 1, that was the square root of 9, which is 3. So we can just pop that in. So 3 on 2 times 4 on 3 minus 1. 4 divided by 2 is 2. Oh wow, the derivative is 1 as well. Well, that's a coincidence. That would almost never happen. I mean, earlier we found that the derivative at the point where x is 2 was 3. Okay. So the tangent slope is 1. So since the slope is 1, therefore the equation must be y equals slope x plus something. So we can say the equation of the tangent is y equals 1x plus c for some c. And because the point 2, 1 passes through this, so we can say 2, 1 is on a line. So when y is 2, the x is 1. And so we get 2 equals 1 plus c, so 1 equals c. So c is 1. And so therefore the equation is, I should finish that off. The equation is y equals 1x plus c. So it's x plus 1. So everything turned out to be, well, not everything. The y coordinate and the derivative and the c turned out to be 1. That was a big coincidence. That would almost never happen. And now we've found the equation of the tangent. Okay, let me do another one, just to make sure you've got the deal here. Find the equation of the tangent to f of x is x to the... Maybe I'll do a polynomial this time. Yeah. So Let's just do a small one like that. Do you know what? I might just stick a coefficient in front of that. Okay, well, x to the 5 minus 3x squared. At the point where x equals, let's pick a number, eh? Well, x equals -1. Okay. Well, we're going to need to find a point on the tangent and the slope. I like to find the point first, so let's do that. When x equals 2, we get f of 2 is 2 to the 5 minus 3 times 2 squared. 2 to the 5 is 32. No, what am I doing? X isn't 2. That's what it was in the previous problem. Pay attention, David. F of minus 1 is minus 1 to the 5 minus 3 times minus 1 squared. Now, minus 1 to the power of 5 would be 5 minus 1's times together, and all those minuses should sort of, pairs of them should cancel out, so we should end up with minus 1. And minus 1 squared is 1, so we get minus 1 minus 3, which is negative 4. So the tangent passes through minus 1 minus 4. Okay. Now also the derivative, now it's a little easier for someone who's reading this who hasn't seen the original question for me to just write down the function again, so it's a little easier to see how we're doing it. So f dashed x is 5x to the 4 minus 3 times 2x, which is 5x to the 4 minus 6x. Okay. And so f dashed x, if we sub in the minus 1, that'll tell us what the slope is. Now, f dashed of minus 1 would be 5 times minus 1 to the 4 minus 6 times minus 1, which is, well, minus 1 to the 4 is just 1, and so that's 5, and 6 times minus 1 is 6, and so we get 11. So the tangent has slope 11, therefore the equation, the tangent is y equals 11x plus c for some c. Okay. And so now we need to figure out what the c is. We do know it passes through the point minus 1 minus 4. So we get minus 4 for the y is 11 times minus 1 plus c. So minus 4 is minus 11 plus c. If I add 11 to both sides, I'll get 11 minus 4, which is 7. And so therefore the c is 7. And so the equation is y equals 11x plus 7. They won't always work out to be whole numbers. They do today. Okay. So that's generally how the process works. If you look very closely at the way I've written the working, I've been very explicit about what I'm calculating at every time, and that's really useful for people who are reading your work. So you've noticed that I've said that when x is minus 1, I've referred to this. I've figured out what f is, and then I've made a conclusion that it passes through this point, so that everyone can tell why I'm doing that. And then I've calculated the derivative and subbed it in, and each thing has got its own piece. And I've used this equals to say it's still equal to the same thing before. If I was reading this aloud, it would be f dashed x, f dashed of x is 5x to the 4 minus 3 times 2x, which is equal to 5x to the 4 minus 6x. And f dashed of minus 1 is 5 times minus 1 to the 4 minus 6 times minus 1, which is equal to 5 plus 6, which is equal to 11. So each equals, after the first one, is a which is equal to. Okay, and so then I said the tangent. Here I've given the reason why, here down here, I've given the reason why I'm doing this calculation here. Okay. Now I did tell you an alternative way, that I would tell you an alternative way of finding the equation of a line that passes through a point. Let me just go back to this diagram on the screen here. I might send my point back to where it was. Oh, there it is. So we noticed that when we move along this line, every one we go across, I mean this is actually every 0.001 we go across, it goes up 0.003. So basically every one we go across, it goes up 3. But that going across is actually how far away from this point we are. So we're not really concerned with what the x is, we're concerned with how much bigger x is than 2. So this distance here, if I drew a point at this point just here, let's actually draw it. If I drew a point at this spot just here, sorry, 2.0016 right there, then I don't really, to figure out what this new point is, I don't really need to know what this x coordinate is. I just need to know how far along it is from 2. So it's the 0.001 I'm interested in. And I can figure that out by subtracting 2. So this bit just here is x minus 2. And this bit up here, well, I know that that is 3 times that distance. And I need to add it onto the 6 to get to the right spot. So I'm just going to do that again over on the document camera. Or to find the equation of the line, we still need the point that it passes through and the slope. Or we could know that every time you move forward from the point minus 1, minus 4 by 1, you go up by 11. And so we can say that the new y that we calculate, so here's the story. I'm just going to actually draw a picture of it. Here's the point minus 4, minus 1, minus 4. And here's my line of slope 11. Now, line of slope 11 is way steeper than that, but it's just easier to draw at the moment the way I am. Slope is 11. If I go across a bit and up a bit, I know that this distance is 11 times this distance, because that's how slopes work. So this distance, if I'm here at the point xy, this distance is x minus 1. And I know that this distance is 11 times x minus 1, because that's how slopes work. And so therefore, I started at minus 4, so I've got to add this on. And so the equation becomes y equals the original y value plus the slope times x minus the x value. And it's totally okay to leave it in that format if you like. And this is how I got Desmos to actually draw my this is how I got Desmos to actually draw my tangent for a moving point. I used this version of the formula because I just needed to put f dashed of some number a, some point x in that spot, and that'd be great. So just so you know, if you've ever seen someone find a tangent this way, that's one of the ways. The other way might be more comfortable to you though, whichever you like. I don't really mind. Some people do mind, so worth checking with whoever you're doing your maths with in the future. Okay. So that's great. I've been able to find tangents using derivatives because the tangent has the same slope as the derivative at that point. But there is one more thing I want to do. The thing is that there are curves that I can draw on an xy plane that aren't the graphs of functions. Oops, sorry. Sorry about that. For example, this curve, a circle, we're familiar with circles, isn't the graph of a function. A function has the property that every time you pick an x, you can figure out the y, and you draw the graph essentially by, for every x, finding the y, and then interpreting that xy as a point, and drawing that point, and then you draw all the xy points, and you get a curve. But what that means is that every x only has one value of y. But on this curve, most of the x's have two values of y. At this x here, there's a value of y here that goes up, and there's a value of y here that goes down. So this is not the graph of a function. Now, I still can talk about there being a tangent to this curve. I can easily think about a line that I might move, and I might move it so that it hits the curve at exactly one point, and that would be a tangent. And I can also still think about the fact that when I'm really close to this curve, it still looks like a straight line. So let me just pick a point on the curve. Let me think. Radius 3. I'm thinking 2 and the square root of 5. Yep, there we go. So here we are at this point, and if I zoom into that point, my curve still becomes approximately straight. Slope's a little harder to guess here. Looks like if I go up 1, it sort of if I go forward 1, it sort of goes down 1. The slope is like nearly 1 at this point. I don't really know. It's going to be some wicked decimal at the point that I've chosen. So there's that, okay? So I could do it, and it's almost straight here, and that would tell me what the tangent is. But the only way I know how to find the correct slope for this tangent is if my curve is made by a function, and my curve isn't made by a function. But I'm lucky because if I draw the tangent at this point, it should, let me step back a bit, in the same way that this function is approximately equal to a straight line at this point, it's also approximately equal to a function. Because look, way back here, long before I got to the point where it looked flat, at this stage, the part of the picture that I can see does have only one x for each y. Sorry, one y for each x. And so therefore, I can hope that there is some sort of formula for a function that will produce at least this bit of my curve. And there is, for this curve, it's this function. That curve matches that function matches my curve exactly at this spot. So if I knew what that formula for that function was, I could differentiate that, and that should give me the slope. this function actually works for about half the circle. If we want the bottom half of the circle, we're going to have to use a different function. But even better, there's a cool magic trick I can do, which is this. I don't even need to know what this formula is in order to find the derivative. I can just imagine that it's possible to find it and imagine that it is there. All I can do is imagine that there is y is a function of x and do my derivatives as if it was. And that's called implicit differentiation. And that's what I'm going to talk about on the paper. So the idea is that a random equation, well, maybe not random, an equation in x and y creates a curve. The equation I had has a circle, but they can get more wickedly strange than that. Actually, let me show you. I'll go back to the original thing. Yep, so I've got wicked thing involving x and y, and it produces this thing. And it might be even weirder if I go further out. No, it's basically a curvy thing with a bump. Yeah. I can even do like this, and this curve has 3 different sections, which is particularly bizarre. So anyway, that was just an idea. It's fun to play with Desmos to see what it produces when you do these things. The idea of doing the derivatives is so that we don't have to draw the graph to be able to figure out what it's doing at these points. So an equation in x and y creates a curve, and theoretically nearby to any point on the curve there is a function which matches the curve. So that y equals f of x matches the curve. And then what we can say is the slope of the curve at that point is the same as f dashed x. I'm going to just give that point a name, x, y, is f dashed x. Okay. And what we're going to do is we're going to imagine that it's there without ever figuring out what it is. So we're going to imagine that every time there's a y, I could, if I wanted to, replace it with the correct formula for f dashed x, and this whole thing would work. So it's easier to see it as an example, actually. Find the slope of the curve with equation minus x plus y to the 5 equals set. Just a second, I'm going to pick a number for that in a second. Just let me do some calculations. I'm going to put a y here. Yep. Ooh. I'm going to need a calculator. I'm just going to pause the video while I figure this out. Okay, I'm back. And I've got an equation that I think works. Let's hope I was right. So find the slope of the curve with equation 8yx cubed minus x minus y all to the 5 is minus 8. Traditionally there'll be something involving x and y equals number, but they don't have to be that. Any equation will do. It's allowed to have x's and y's on both sides. With that equation, at the point 1, 3. Okay, so the first thing we should do is check if the point 1, 3 really is on this curve. Otherwise, the whole question doesn't make any sense. You can't find a tangent, you can't find the slope of the curve at a point that isn't even on the curve. And so I need to check that first. So check it's on the curve. And if it is on the curve, when I sub 1, 3 into this formula, it should come out to minus 8. So 8 times 3 for y times 1 for x cubed minus 1 minus 3 to the 5 is 24, because 1 cubed is 1, minus 2 to the 5. It's not on the curve. Because I've got 24 minus 32, which is so not minus 8. 24 plus 32 would be 56. Okay, so it's not on the curve. Damn it. Right. And so at this point you would say, I'm actually going to write it down. So 1, 3 is not on the curve. So the question doesn't make sense. Okay, so what if we had chosen our curve to be 56 instead of minus 8? Find the slope of curve equation 8yx cubed minus x minus y to the 5 equals 56 at the point 1, 3. So first we'll check that 1, 3 is on the curve. So 8 times 3 times 1 cubed minus 1 minus 3 to the 5 is 24 minus 2 to the 5, which is 24 minus 32. So when you do an odd power, when you do a power with an odd exponent on a negative number, the answer is still negative. And 24 minus 32 would be 56. So yes, it is on the curve. Okay. I'm glad I got it wrong first time so that I would see you how to react. Okay, so yes, it is on the curve, and so it makes sense to find the slope of the tangent. What we're going to do is that, well, the slope of the tangent should be the derivative of whatever y function of y is nearby to that point. And so you don't have to mention that whole story to do this. You can do implicit differentiation. So you can tell the reader that that's what you're doing. And so I'm going to rewrite the curve so that we don't forget where we started. This is the equation of the curve. And we're going to differentiate this as if y was a function of x. So secretly inside the y we are imagining that every one of these y's is the same formula, f of x, but we don't know what that formula is. Okay, and remember that f dashed x is perfectly acceptable, but so would dy on dx be. And this is how we normally do this thing. So, the way we normally do it is with a dy on dx. So we're going to differentiate these as if the y was a function of x, so we're going to do each piece separately. So this piece, the 8 is a constant multiplied on, so it will still be there. The y is something involving x, and the x cubed is something involving x. So these two things both involve x. So I'm going to have to treat this as a product rule because the y is a function of x. Okay, so I'm going to use the product rule here. So I'm going to see it as 8y and x cubed. The derivative of 8y would be 8 because it's multiplied on times whatever the derivative of y is. Because I don't know what y is, so the only choice I have is to write it like this. And then I keep the x cubed. And then I'll keep the 8y and I'll differentiate the x cubed, which would be 3x squared. That's the derivative of this bit. Okay. I'm just going to put that in brackets so it's easier to see that it came from one thing in the previous line. Now let's do the derivative of this. Well, that's something on the inside times to a power, so I can use the chain rule. So thing to the 5 would become 5 thing to the 4. But because of the chain rule, I will have to multiply by the derivative of this. The derivative of x is 1, and the derivative of y is, well, whatever dy and dx is. And then finally, the derivative of a single number is 0. Now the reason this process works is that whatever this quantity is, if I'm on the curve, it will always be 56. So if I figure out how quickly this quantity changes when x changes, it should be the same as how quickly 56 changes, which is none. And that's why it comes out to 0. Okay, and now I have this wicked formula that involves x's and y's and dy over dx. So the dy on dx is what we're looking for. That's the slope we want. It is the f dashed x if y was equal to f of x. And so we want to rearrange this to get a formula for dy on dx. So I'm going to have to free those dy on dx's from their brackets to be able to get where we want, but I'll do the minimum amount of work I can. So let's see, we have 8x cubed times dy on dx here, and we have 24yx squared here. We have a minus, now here's interesting, I do not want to expand that out, I'm going to leave it as it is. But I do notice that I can do this times both of these, and I need to include the minus 5. So let's see, we have minus 5x minus y to the 4 times 1. And then minus 5xy minus y to the 4 times dy and dx. Times minus dy and dx. And that's equal to 0 still. Okay. Now what I'd like is to just have dy and dx equals. And so I notice that there are some pieces here that aren't actually attached to a dy on dx. I'm going to move them out the way so it's a little easier to see where the dy on the dx's are. So if I subtract this, it won't be there, and if I add this, it won't be there, but they will end up on the other side. So let's see, we have 8x cubed dy on dx plus 5x minus y to the 4 dy on dx is minus 24yx squared plus 5x minus y to the 4. Okay, we're doing well. And now I notice both of these terms have a dy on dx. So if I factorize that dy on dx, this thing with a dy on dx, then there would be one of them and it would be easier to see what's going on. No, one of them written on the page. So if I remove the dy on dx, these two pieces are what's left. And so I get the dy on dx here. So this times that is the same as this. That works. And I get minus 24yx squared plus 5x minus y to the 4. Okay. And so I now have that dy on dx. If I divide by this, it won't be there anymore. So I can have minus 24yx squared plus 5x minus y to the 4 over 8x cubed plus 5x minus y to the 4. And that is what the slope is. Interestingly, the dy on dx you would normally expect to be a formula involving just x. And technically it is, because each of these y's is some sort of function involving x that I could sub an x into to figure out what it works out to. But I already know that at this point on the curve, the point 1, 3, I know what the y works out to. It works out to 3. So at the point 1, 3, x equals 1 and y equals 3. And so the dy and dx at that point comes out to minus 24 times 3 times 1 squared plus 5 times 1 minus 3 to the 4 over 8 times 1 cubed plus 5 times 1 minus 3 to the 4. So 24 times 3 would be 60, 72. Minus 2 to the 4 would be 16. 5 times 16 would be 80, so we get 8 on, now 8 plus 16 would be 24, which is 1/3. So the slope at 1, 3 is 1/3, which is a total coincidence. It does not almost never works out to be the x divided by the y. Okay? Just, that's a coincidence. Okay. And what that means is that the slope of the curve at that point is 1/3, so that for every x you move over, the y goes up 1/3 of that. I would like to just check that on the Desmos. You can't normally do that if you're in, say, an exam situation at university, but I can do it here. So what was my curve equation again? It was 8yx cubed minus x minus y to the 5. 8yx cubed minus x minus y to the 5 equals 56. Let's turn it on. And that's what that looks like. And I can put the point 1,3 in. That's 1.3. And that's this point here. And when I zoom in on that, oh dear, I'm not getting 1/3. I think I might have done something wrong along the way somewhere. Because when I draw that thing, I do not. If I go across 1, it should go up 1/3, but it's going up like a lot smaller than that. So I've done something wrong. Let me just go back and see if I can figure it out. Oh, it's not 16 just here. It's 5 times 16. And so that's not 8. This is still 8, but that's not 24. That's 8 plus 8, 80, which is 88, which is 1/11. Right, fixed. Okay. So back to here, let's see if the 1/11 makes sense. That would tell me that if I went across 11, it should go up 1, right? 1/11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and it went up 1. Yes, that's the slope as it should be. Good, we're working well. Okay, cool. Well, we can use this now that we know how to find slopes of general curves. We can use this to find the tangent to a curve at a particular point. And actually there is one more thing that we can find, not just the tangent, but the normal. So I'm just going to define something. So we know that the tangent at a point has the same slope as the curve. The normal to a curve at a point has the has a slope, is a line that's perpendicular. Is a line perpendicular to the tangent. So if I go back to this picture just here, if I want something that takes 11 to go up 1, if I want something perpendicular, it should go out this way, and if I go back 1, it should go up 11. So its slope should be minus 11. Let me just draw both of those. Y equals 3 plus x minus 1 times the slope, which was 1 over 11. So that's the tangent. And y equals 3 plus, now just a second, it should be minus 11, shouldn't it? And that's the normal. It's perpendicular to the curve. If I zoom out, there's the curve. This line's perpendicular. This line's following the curve. And that's called the normal. And a useful piece of information about normals and tangents is that if two, or just any lines, if two lines are perpendicular, then their slopes, if the slope is written as a fraction, you'll turn it upside down and minus it. Okay, so it's the negative reciprocal, it's called. Or if you like, when you multiply them, you should get minus 1. So note, if two lines have slopes, it's traditional to use M1 and M2. The lines are perpendicular when M1 times M2 is negative 1. Okay. And what that means is that the slope of the normal is minus 1 over dy and dx. Is that. And since I know its slope and I know a point it passes through, I can figure out its equation. Okay, so that's all useful information there if I want the normal and the tangent to a curve. Normals are useful because they can tell us which way to go to get as far away from the curve as quickly as possible. Things like, it's useful in astronomy for those sorts of things. Okay, so I'm going to do an example now where I have a curve and I find both its tangent equation and its normal. And I think I have enough time for 2 examples. So I'll see how I go. To the curve with equation x squared plus 3xy minus y cubed equals that's needed to. Sorry, just a second. It's taken me a while. I want to get it right this time. Yep, okay, cool, this works. Find the tangent and the normal to the curve with equation x squared plus 3xy is y cubed minus 1 at the point 2, negative 1. Okay, so first what we're going to do is we are going to just check that that point really is on the curve, or this doesn't make any sense. And also I'm just going to have a close look at this. It says find the tangent and the normal. I mean, that's saying find the line, which is the tangent, and find the line, which is the normal. And it hasn't really specified the way that it wants us to present that information. But when a mathematician says find the tangent, what they mean is find an equation for the tangent. Okay? So it's not just asking me what the slope is, because the slope is not enough information to tell me the tangent. I really want to find the equation. Just pointing that out. So first let's check that 2, negative 1 is on the curve. So let's see. The left-hand part of this equation is, I'm just going to write, if xy is equal to 2, negative 1, then x squared plus 3xy, which is the left-hand part of the equation, would be 2 squared plus 3 times 2 times minus 1, which is 4 minus 6, which is negative 2. And y cubed minus 1 is negative 1 cubed minus 1. And negative 1 cubed is minus 1. And so we get negative 2. And so they both work out to the same answer, so yes, it is on the curve. Therefore, x squared plus 3xy. So yes, 2 minus 1 is on the curve. You'll notice that last time when I did this, I subbed it into one side and it came out to an answer. In this one I subbed it into both sides and they came out to be equal to each other, and so that worked. Okay, so I checked that that's on the curve first, and so therefore it makes sense to calculate a normal and tangent. And now I need to figure out the slope of the tangent and the slope of the normal, and I can use that information to find their equations. Okay, so now I'll do some implicit differentiation. Okay, so we started with x squared plus 3xy is y cubed minus 1. So we'll differentiate everything. So the derivative of x squared is 2x. The 3xy, well, since the y is secretly a function of x, I'm going to have to use the product rule. So let's see. I'll do it in these pieces. The derivative of 3x is 3, and I'll keep the y. And then I'll keep the 3x and differentiate the y. Okay? Now that y is secretly a function of x, so it's like brackets thing to the power of 3. So if that was an x, it would be 3 thing squared, and the thing is y. And because of the chain rule, I have to do the derivative of the inside, and the derivative of the inside is dy over dx. And of course the derivative of 1 is 0. Okay, so I want to move everything around so that all of the dy and dx's are on the same side. So what I'm going to do is I'm going to keep this here, and I'm going to remove these things by subtracting them, and I'm going to move this over there by subtracting it. So that's a lot of things all at once, but it's okay to do that. Like that. All right? And now I'm going to factorize this out. 3x minus 3y squared. I do notice they both have a 3 actually, and I feel like factorizing that now because I think it'll make things simpler later. Okay? And these both... Okay. I guess they both have a minus in them. Yeah, let's do that too. It's not necessary, I just... makes me feel better. Okay? And so now my dy on dx becomes 2x plus 3y over 3x minus y squared. So now I have a formula that if I know the value of x and the value of y at this point, I can sub it in there to get the answer. So at the point, what was it called? 2, -1. dy on dx is, all right, let's see, we've got 2 times 2 plus 3 times -1 over, 3 times 2 minus -1 squared. So we've got minus 4 minus 3 over 3 times 2 minus 1, which is minus 1/3. Oh, okay, cool. So this is the slope of the tangent. And of course the slope of the normal has to be arranged to be perpendicular to that. And I know that two slopes, when they're perpendicular, multiply to give -1. And the thing I would multiply this by to get -1 is 3. But you can also think of it as minusing that and flipping it over. Well, some people think of it like this. Which is 3. So you can write that working down, or you could just straight up write it as minus like 3/1. So you could skip straight to there if you want. So if this had worked out to be 5/6, then you would have got 6/5. If this worked out to be minus 5/6, then the slope of the normal would have been 6/5. Yeah, and if this had worked out to be plus 1/3, this would have worked out to be minus 3. So now I know the slope of both the tangent and the slope of the normal, which means that I can calculate their equations. So the equation of the tangent is, now let's see if we can figure it out. It starts, the y value starts at -1, and then we put the slope times x minus 2, because we figure out how, the y value starts at -1 because that's the y coordinate here, and then we go off the slope times how far from 2 we are. And the equation of the tangent is y equals -1 plus 3x minus 2. So they both start at the same place. They both are measured relative to x minus 2, and you just use the different slopes. If you wanted to, you could expand these out to get a traditional equation. And also, if you wanted to, you could do the traditional method where you go, well, the slope is 0, where the slope is minus 1/3, and it'll be like minus 1/3 x plus c, and sub in a point to figure out what the c is. Okay, so I've got a few minutes left, and I just want to do one more example. And give me a second to figure it out. Okay, so let's find the tangent and normal to the curve with equation x minus 2 squared plus y squared equals 9 at the point where x at the point 2, 3. Okay. So what we would do is we would set up implicit derivative, we should check if this point really is on the curve. 2 minus 2 squared plus 3 squared is 0 squared plus 9, which is 9. So it is on the curve. Implicit derivative. Implicit differentiation. So the derivative of x, so I'll just write it down again. The derivative of this, well, chain rule would tell me it's that times 1. Chain rule on this would be 2y times the derivative of y. And the derivative of 9 is 0. And then this one's actually a lot easier to calculate. 2y dy on dx is minus 2x minus 2. I can cancel out the 2's, and so dy on dx is minus x minus 2 on y. Okay, and so at the point 2, 3, dy on dx works out to be minus 2 over 3, which is minus 0 over 3, which is 0. Now a line of slope 0, well, let's just do it. So the tangent has equation y equals that plus 0 x minus 2, which is just y equals 3. And that's what the equation of a horizontal line is. It has slope 0, which means that for every x across, the y doesn't move at all. So the y is always the same, so the y is always 3. So I could have actually said that once the slope is 0, I could have skipped straight to the y equals 3 if I wanted. But this is an issue because 1 over 0 is infinity, it doesn't exist. And so I can't use this kind of equation for the equation of the normal. But that's okay because every point, the perpendicular to a horizontal line should be vertical, and every point on a vertical line has the same x coordinate. And so you can use the equation of just x equals whatever that x coordinate is. So we can say the tangent is vertical, tangent is horizontal. So the normal is vertical. So the equation is x equals 2 since it passes through 2, 3, and therefore it must have the same, they all must have the same x coordinate. All right, that's enough. Thank you very much for listening. I hope that was helpful to you.